Okay, welcome back to lecture 13. I will just like to begin with a quick review of the last lecture. Class we tried to derive the zeta potential associated with a surface in contact with the liquid phase. Okay. We also tried to kind of interpret how the dual layer comes into existence. Why is it that the charges in the solutions get distributed and forms what you know as the bulk charge or the diffuse layer of a solution, and then we try to also calculate the potential as a function of distance as you move away from this double layer into the bulk layer. We try to use this concept of double layer charging in order to realize a certain type of microfluidic flow called electrosmotic flow. Again, just to review that if there is a surface which has a certain set of dangling bonds, like let us say silanol bonds on a silicon surface SiOH, and it comes in contact with a solution of a certain pH, there is a tendency of that surface to acquire a charge that could be net negative charge or positive charge depending on if the pH is acidic or basic. Because of this charge, if you are able to place a solution close to this charged surface, there is always going to be this diffuse layer which is formulated. If we talk about microcapillaries with carved in such kind of surfaces with charges and try to flow fluids across it, there is going to be some kind of comparative between the dimension of the channel and the thickness of the diffuse layer. Now, this results to also this also tends to drag the diffuse layer also tends to drag the fluid in such a microcapillary when you put an external EMF across it. So, we try to derive some equations and formulations related to this flow process, the electrosmotic flow process, and basically we also tried to look into you know the Couette's flow just for a comparison of this electrosmotic flow with a flow wherein there is a, let us say, two plates with one fixed and another moving and trying to drag a fluid layer along with it, and then compare it also to a parabolic flow where there is a pressure gradient and two fixed plates between which the fluid flows. Okay. So, we kind of saw that in case of electrokinetic flows there is always a tendency of the flow to develop a plug like behavior. So, the velocity profile is like a plug. Okay. So, in case of pressure driven flows it is something like a parabola. So, if we consider and try to start from that aspect, we found out that by solving Navier-Stokes equations. Okay. So, basically we kind of tried to make a comparison between the different profiles, the velocity profiles within such channels when the flows are pressure driven as opposed to maybe when the flows are electrokinetic in nature. And we also tried to ascertain what happens in case of a pressure gradient across such a capillary with two sides fixed or two plates fixed, and try to derive an equation of velocity and the variation of velocity with respect to the y direction. Okay. So, essentially the function that we obtained for u on the velocity in that case was also minus 1 by 2 eta dp by dx h square times of 1 minus y square by r square h square, where dp by dx essentially is the pressure gradient across the capillary in the x direction, and we assume that the plates, the two plates are respectively fixed at y equal to plus h and y equal to minus h. The middle of such a plate assembly is really the y equal to 0. So, if you plot the u with respect to the y, essentially you get a parabolic profile, the square on the y, right. So, there is a flow velocity variation of this parabolic type, and this makes sense also because the velocity here very close to this channel wall is 0 on either sides, and it is maximum somewhere at the center of the channel. Okay. So, if y equal to 0, the u becomes u maximum, which is 1 minus 2 neta dp by dx times of h square. This is the maximum velocity that one can have in such a channel flow. So, if you assume a little bit of different sign convention in which the plates are laid, in the way the plates are laid, and assuming that 2h essentially is equal to a, or that the distance between these two plates 2h is nothing but a. So, in that case h becomes equal to a by 2, and u max in this expression is 1 minus 1 by 2 neta, okay, del p by del x a square by 4, also 1 minus 8 neta del p by del x a square. Okay. That is what the u max or the u maximum would be in a case like this. Let us now try to find out the maximum flow rate which would happen because of this function u. Okay. So, if we really look at the flow rate, we can assume that in this particular case there is a circle, or there is an annular of area A through which the fluid is emanating out, all right, at a velocity u, which is given by the function shown earlier in terms of the pressure gradient, the square of the y and the square of the distance from the mean plane, or y equal to 0, y equal to plus h and minus h. Okay. So, if we look at the differential, let us suppose this value here is y, okay, this distance here is dy, and we want to find out what the area vector is. So, the area here would essentially be pi y plus dy square minus pi y square. So, it will be also equal to twice pi y dy. Okay. That is what the dA of this particular annular of fluid would be. Okay. And we already know that u essentially as a function of y has been represented earlier as minus 1 by 2 eta dp by dx r square times of 1 minus y square by r square. R is the radius in this case, by the by, okay, which is also equal to h. And so, if you want to find out what is the volume flow rate, or phi, this becomes equal to 0 to r minus 1 by 2 eta del p by del x r square times of 1 minus y square by r square. Okay. This is the u value times of 2y dy. As you also know, dV by dt, the volume flow rate, is nothing but the velocity times of area. All right. That is exactly what this is about, and the integral we assume takes place between 0 and r, which is the radius of the capillary. Okay. So, essentially if you just solve this equation, you were left with, so you can take this twice neta del p by del x and r square and twice pi outside the integral 0 to r 1 minus or r square minus y square times of y times of dy, and there is a divided by r square here. These two cancel out and you are left with minus 1 by 2 eta dp by dx 2 pi, and this happens to be r square y square by 2 minus y 4 by 4. Okay. That is what the integral is, and between 0 and r. So, essentially this takes the form r square by 4, and we are left with an equation of the type phi equals minus 1 by 2 n del p by del x, okay, 2 pi times of r 4 by 4. Now, one thing which is of importance here to be seen is that, essentially we considered a channel at the very beginning. If you consider the electrosmotic flow of length L, okay, so essentially you considered the channel of length L, and if you assume that there is a pressure driven flow in this particular example, which is essentially between the length L and the pressure gradient in this case is P, then dP by dx can be represented as P by L. Okay. So, if I put back the P by L into this particular equation here for the pressure driven flow case, phi becomes equal to 1 by 2 minus 1 by 2 n, give me a minute, minus 1 by 2 eta dP by dr times of twice pi, this is dP by dx times of r 4 by 4. Okay. And essentially dP by dx is nothing but P by L here. So, we get phi is 1 by 2 eta P by L twice pi r 4 by 4, and if we just readjust this equation, pi comes out to be equal to pi P r 4 divided by 8 times of eta L. Okay, that is what the volume flow rate is in this particular example. And one more issue here is that if you consider what happened in the electrosmotic flow case, the zeta potential for the electrosmotic flow, the EOF, okay, this was derived as 4 pi eta phi times of k divided by di, where k is the conductivity of the medium, phi is the flow rate, eta is the viscosity, I is the current, d is the dielectric constant. And if we just substitute this value of phi here, assuming that we equate the electrosmotic flow with the pressure driven flow, we have a situation wherein we have this 4 pi eta di times of pi P r 4 divided by 8 eta L times of k, all right. And all this essentially can be further reconverted a little bit. If you remember from before, the value of k is also equated or assumed to be the ratio between the current I, the area of cross section Q, and the electric field X. Okay. So, that is how we found this relationship earlier from the famous R equal to rho L by A term, and then using V equal to I R Ohm's law. Okay. So, essentially if we substitute the value of k here in this particular expression, let us find out what it would finally look like. One thing which is very important and very critical to mention here is that since zeta here is equal to this particular term 4 pi eta di times of pi P r's r 4 divided by 8 eta L times of. So, here we can find out tentative relationship between zeta and the pressure. Okay. So, you have a case where you have pi square times pressure P r to the power of 4 divided by d I L, and then of course, there is a k term here, okay, which automatically means that the zeta potential in this particular case would relate to the pressure of the medium P by the relationship P is equal to zeta times of d I L divided by pi square r 4 k What does it really mean is that if you consider a pressure driven flow analog of the electrosmotic flow, okay, the pressure driven flow analog of the electrosmotic flow. What I am trying to indicate is that if you have, let us say, an electrosmotic force which is flowing the fluid in the capillary, and you consider that to be, you consider that to be essentially within the same flow rate, everything contributed by an equivalent flow with a pressure gradient, we can make an analogy between what kind of zeta potential is needed for creating what kind of flow pressures. Okay. And here, as you see, if the zeta potential of any surface is more, as in this equation, the pressure of the flow would be more, and vice versa. Okay. So, that is a very interesting observation which we will kind of carry forward later. Here, if we substitute the value of k into this particular equation here, okay, let us look at how this would really behave. So, in this particular case, and I need to actually substitute the value of k here, we get P equals zeta d I L divided by pi square r 4, and k is essentially I by q x, right, and q is pi r square. So, I times of pi r square in the numerator times of x. So, we can actually do these cancellations here. R 4 cancels into R 2 and pi cancel out. So, we are left with essentially the terms zeta d L x divided by, and of course, there is going to be a 2 here, which we forgot, because essentially there is a 2 here in the denominator. So, there is a 2 d I L in the denominator here. So, twice zeta d L x divided by pi r square is what this effectively would look like. All right. So, essentially one important thing here is that the pressure that is generated from a flow channel with a zeta potential, let us say z, is also inversely proportional to the area of cross section of the particular channel. All right. So, the pressure head P imparted by the electrosmotic flow can be equated using this kind of a formulation, which I would just like to write. So, therefore, in summary, we would like to write down that the zeta potential is equated to 4 pi eta phi k by d I is also equated to the pressure as P is twice zeta L d I divided by pi square r 4 k is also equated again as twice zeta L d I, L d x, twice zeta L d x divided by pi r square, the area of cross section. This is essentially the equivalent pressure, okay, of an EOF channel. So, you can consider the amount of pressure head that is imparted onto the fluid by virtue of the EOF or the electrosmotic flow is essentially this P. Okay. So, I can say that the pressure head which is imparted by the EOF is given by equation 2. All right. So, there can be design problems wherein you want to find out what kind of pressure any EOF flow gives, and so essentially you need the parameters like the zeta potential of the channel, the length of the micro channel, the dielectric constant of the medium, the field which is across this channel, and then finally the radius of the capillary, microcapillary into question. So, let us shift our attention to the second electrokinetic phenomena, that is the streaming potential. Okay, as we talked about before, the velocity of a liquid flowing through a capillary has a parabolic profile, right, with a y which varies as the distance from with a v that varies as the distance from the center of the tube to the sides. Okay. This essentially is v, this is v, all right, the velocity. So, if you just remember back the various ways and means of predicting the various electrokinetic properties, there can be a case where you produce or give a pressure driven flow, and it creates a set of charges on the walls, or set of currents, and there is a case when you apply an EMF from outside and it generates a flow. Okay. So, in one case the cause is the EMF, in another case the cause is the flow. So, flow generates EMF inside the channel, a flow generating EMF inside the channel. The phenomena is also known as streaming potential. Okay. So, the liquid at the surface of such a flow being stationary leads to the double layer at the interface consisting of a stationary phase and a mobile phase, the solution, and the relative motion or movement of these two planes of the double layer, one stationary with respect to the wall and another moving with the fluid, would give rise to the movement of the charge and generate a potential. So, let us derive what this potential level would be in such a microchannel case. So, let us say we have a parabolic flow taking place within this particular architecture here, and the velocity flow profile is also indicated by this particular parabola. Okay. Well, the maximum velocity is at the center, and then these velocities at both sides of the channel are essentially in the no slip zone. So, they are 0. So, u here, the velocity is kind of also defined as p times of r square minus y square by 2 eta L, right. P is the pressure, r square minus y. So, this is again what we found out from the parabolic flows, right, P by eta L r square minus y square. So, if we put this liquid through a pressure difference, or push this liquid through a pressure difference across this channel, there is going to be a double layer which is generated, and in that case we can model the flow pretty much like this figure right here. Okay. So, if you see here, there is a double layer of charges which are created on both sides. One is a stationary layer, which is the positive layer in this case. So, this is essentially the stationary layer of charges, and the other is a mobile phase, which is the negative charges on the solution. So, whenever there is a fluid flow by means of a pressure, these charges, this positive layer being stationary and the negative layer being mobile, they move relatively with respect to each other. Okay. So, let us assume that this delta B, this thickness of the double layer, right, and let us also assume that r be the radius of this particular channel. So, essentially r is the distance from the center of the channel all the way up to the wall of the channel, and we decipher a parameter x here, where x is equal to essentially r minus delta. Okay. And in this particular case, the u, the velocity, which is actually represented as p divided by 2 eta L times of r square minus y square, can be represented in this case if I substitute the y by the equivalent r minus delta. Okay. So, this is actually, let us say this is y in the notational, just for notational consistency, this direction is the y direction and this is the x direction. So, this is actually y, and this essentially is also y equals r minus delta for notational consistency. So, r square minus y square can be represented as p by 2 eta L times of r square minus r minus delta square, and if we do this or if we try to calculate this, we are left with 2 r delta minus delta square. Okay. And delta being very small, we have already mentioned that essentially delta, the charge, the dual layer thickness is around tens of nanometers, and so therefore, this delta square is very small in comparison to twice r delta, can be safely neglected, and u essentially in this particular case would be nothing but p times of twice r delta by 2 neta L, or p r delta by neta L. Okay, that is what the u is going to be. The u delta is going to be in this particular case, okay, the velocity across this double layer. Now, as we need to consider that at the movement of the front of the liquid forces over these layer of charges on which on the surface essentially produces a current, okay, and this current is also given by the product of the total charge around a unit length, okay, of the tube and the velocity. So, if you have, let us say, a certain surface charge distribution in terms of charge per unit area sigma, okay, and in a unit length, that means you have the charge density in terms of per unit surface area, but essentially the total amount of charge we are considering only on a unit length. So, that particular charge times of velocity, that means how many such unit lengths the relative movement of charge is happening over the surface would comprise of the current. So, let me just explain this in a little more detail. So, let me explain this in a little bit details here, that suppose you have capillary of length L and radius r, right. This is the radius r and length is L, and we have a surface density of charge inside this capillary as sigma, surface charge density. Now, the total charge contained in this capillary is given by sigma times of 2 pi r times of L, right, 2 pi r L being the surface area, the internal surface area of the particular capillary. So, if I consider a per unit length of this total charge, okay, so the total charge per unit length, that comes out to be sigma 2 pi r, right, and this essentially if multiplied by the velocity would mean that if suppose velocity is x meters per second. So, this per unit length moves so many times in a second. So, essentially it is charge per second, okay, and that is what current is defined as. So, therefore, let me just write this down in totality, that as the movement of the water front forces over the dual layer, okay, a current is produced and this is also given by the product of the total charge around a unit length of the tube and the velocity of the moving part of the layer. So, the total current I in this case would be sigma times of 2 pi r charge per unit length times of lengths per unit time u delta. Substituting the value of u delta from the derivation made earlier, we are left with u delta is p r delta divided by eta L, as you found out from the case of the pressure driven flow, and therefore, this current I in this case is nothing but twice sigma pi r square p delta divided by eta L. Okay. So, let us assume that if the liquid in question has a conductivity K, liquid has conductivity K, and we already know the relationship R equal to rho L by A, right, and essentially K, which is 1 by rho, is nothing but R L divided by R A. Okay. So, A in this case of course is nothing but the radius square times of pi, the cross sectional area of the circular capillary, and essentially the K, the resistance R of the channel is L divided by K times of pi r square, right. In other words, the conductance, which is the reciprocal of resistance of the liquid, in the microcapillary is just the inverse of that, that is pi r square k by L. Okay. So, the streaming potential E s developed because of this current, and current is formulated by the motion of the charge across the dual layer, is given by I times r, I times L by pi r square k, right. And if we further try to put the value of current here from the previous derivation, which we obtained as 2 sigma pi r square p delta by neta, this term here was the I. So, here the final expression would come out to be 2 pi r square sigma delta p by neta L times of L by pi r square k. These go off, the L's go off, and we are left with a term twice sigma delta p by eta k. Okay. So, that is what the streaming potential would really be. So, one important point here to be mentioned is that you can easily find out from this potential the length delta, the thickness of the dual layer, which can be of immense utility in almost all electrochemistry. So, that essentially is what the streaming potential is in case of a flow just flown through a pressure gradient over a surface, over a dual layer of the surface. So, when we are talking, so we have already derived the streaming potential here E s in terms of 2 sigma delta p by n k. Let us modify a little bit in terms of the zeta potential, try to involve what the zeta potential of such a channel would be, a surface would be. So, as we know from earlier equations that the zeta potential of such a system of micro channel in contact with a liquid phase is also given by 4 pi sigma delta by d. Sigma is the surface charge density, delta is the double layer charge, double layer thickness, d is the dielectric constant of the medium of interest. So, if you just do a little bit of mathematical manipulation here, sigma s sigma delta comes out to be equal to d times of zeta by 4 pi, and essentially if you have had a look earlier at the E s, the streaming potential, it came out to be twice zeta d p, the pressure, divided by 4 pi eta k. Okay. So, if we just try to substitute the value of this delta into sigma into this particular equation here, we are left with that, let us say d zeta is also equal to 4 pi delta sigma. Okay. And essentially from the E s value, if you substitute this 4 pi sigma delta p divided by 4 pi eta k, okay, you are left with twice sigma delta p by eta k. So, essentially that is what E s or streaming potential would result in, and we can also write this down as E s, the streaming potential per unit pressure, which is given as a difference between the both ends of capillary, which is causing this fluid to move, is also twice sigma delta divided by n k. Okay. And essentially that is what is the final form of the ratio between the streaming potential and the pressure. All right. So, another interesting thing here to find out is that if you really want to write these whole terms in terms of quantities which are measurable. So, let us actually try to understand this more in terms of measurable quantities like flow rate phi, then things like measurable quantities like current across the microcapillaries, so on and so forth. So, there would be a little modification though which we will be needing here. Let us resubstitute back this value of sigma delta back into this equation. You are left with essentially twice d zeta divided by 4 pi eta k, right. And we can easily find out a correlation between the potential phi, the flow rate phi and the current I by looking at the equation that we had derived earlier, which talked about the relationship between the zeta potential and these other parameters 4 pi eta phi k divided by d I. Okay. So, if you try to kind of readjust these parameters here, you are left with the value of phi, the flow rate, as d zeta I divided by 4 pi eta k, right, and this can also be represented as phi by I is d zeta by 4 pi n k. This quantity kind of looks similar to what this is. So, essentially S by P here is nothing but twice this quantity here phi by I. So, if you can measure the flow rate in such a streaming flow and also measure the amount of current that is produced, this can easily give you this ratio ES by P, and ES is the streaming potential and P is the pressure. So, if let us say the pressure gradient that were driving or the pressure difference that were driving the flow is P, and phi was the flow rate which was created and it generated a current I, you could easily back calculate what is the streaming potential in that particular application, right. So, that is what is used sometimes as a sensing mechanism for investigating the combinations of surfaces and their behavior with respect to flowing solutions. Okay. So, let us try to summarize that in pressure driven flows, essentially the flow profile is parabolic in nature, right, and there is a no slip boundary condition at all the walls or the edges of such a channel. The flow profile pretty much looks something like this right here, right. You have like a parabola with a velocity which is maximum at the center and which is actually 0 at all these different walls. So, electrokinetic flows on the other hand, electrophoresis, electrosmosis and dielectrophoresis, and these are some of the mechanisms for doing electrokinetic flows. This right here is a simulation by Jaeger's group up at the University of Washington, and essentially if you just compare the flow profiles which are generated from the EMF and a parabolic flow, if you may recall, in a pressure driven flow the flow profile is something like a parabola of this sort, right. So, the velocity vectors kind of keep on maximizing as they go from walls towards the center of this particular capillary. On the other hand, for the EOF flow or the electrosmotic flow, as we know, the flow really takes place as a plug flow from the start of one double layer, which is essentially this side here, all the way up to the other double layer which is on the other side of the channel. So, this area is having a constant velocity, right. So, let me just use a different color here to represent the flow rate related to, or the flow velocities related to the the electrosmotic flows. So, if you see here as represented by these yellow color arrows, these are the flow vectors between the double layers essentially in an electroosmotic flow. So, it is like a plug flow, all the velocities between these two double layers starting from here all the way up to here are uniquely similar to each other, as opposed to the parabolic where there is a slow increase of velocity as it goes from sides all the way to the center. Another interesting point here is the behavior of the flow rate around the surface in question till the double layer starts. So, this is essentially the Helmholtz plane. Okay. We have been talking about this a lot off and on, the Helmholtz plane. So, this particular layer here, as you see, is though having a kind of parabolic profile, which means that this is the layer which is shears to give way to this plug like flow. Okay. So, the velocity really close to this surface here is 0, and the velocity here is some value, maximum value v, and the flow profile between the two are really parabolic on both sides. So, that is how you interpret both these electrosmotic flows and the parabolic flows. Now, there are several important issues which emanate from this, that the electrokinetic flows being a plug like flow, there is always almost a continuity of or a uniformity of velocity vectors across such a channel. right. For characterization's sake, particularly when you do particle image velocimetry, it may be of immense utility if the flow in cross section of such a channel is having all uniform velocity. Okay. This also would mean that these kind of flows do not lead to any particulate separation, particularly when the particles concerned are all different sizes. So, if there are parabolic flows, as we have seen in cases of channels which are pressure driven essentially, one aspect that comes into picture is that if suppose there are different say cells of all different sizes moving across such channels, with the continuity and with this velocity variation in the parabolic profile, the heavier masses tend to move towards the side and the lighter masses tend to kind of move more towards the center by the principle of conservation of momentum. Ultimately, the retentate here at the center is all consisting smaller entities, and the retentate at the sides here all containing the bigger entities. This is known as leukocyte. This is also known as margination. Okay. In the human body, the microcapillaries essentially do this job, where leukocytes which are heavier in comparison to the RBCs would migrate slowly to the walls of the capillary and would be rich on towards the vasculature's walls essentially. Okay. So, that is sometimes an advantage, okay. But then in some cases it may be desirable to move these kind of different sizes and masses throughout the microchannel uniformly without this separation coming into picture. So, electrokinetic flows are the best in those kind of cases, because they essentially do not have any any velocity variation. It is a plug like flow like behavior. Okay. So, this kind of talks about what happens on a silicon dioxide surface. I have been repeating it off and on. So, you can see here that on a silicon dioxide surface, first of all the surface gets hydrolyzed and then later on forms a SiO minus, and there is a net negative charge on the surface, due to which there is a positive charge of counter ions which is developed in the bulk as bulk charges or diffuse layer charges. And then when you apply a potential across it, all these bulk charges try moving towards the negative electrode, thus dragging the fluid around it. And so, therefore, electrosmotic flow in silicon microchannels is a great area of study. Okay. So, some important observations here as summary: the flow rates of such flows proportional to the dielectric constant epsilon, the electric field external to the channel, the zeta potential of a surface, and also proportional to the area and inversely proportional to the viscosity of the particular medium which is flowing through these surfaces. So, essentially depends on the charges at the interface, and there is a counter ion accumulation and which actually drags along the fluid along with it, and it results in a plug like flow. Okay. Electrophoresis on the other hand is the motion of charged particles directly in a fluid medium, and we will be dealing with this a little bit later in more details. But let us look at one illustration here where we can use this electrokinetic techniques for designing micro pumps. Okay. So, in this particular problem here we want to design somehow electrokinetic pumping network. Okay. So, using this principle of double layer and formulation of charge etc. on the surface and the bulk of the fluid, we would like to design a pump network here. So, the dimensions that are given is basically that the circular the microchannels are circular in nature, they are etched in glass of course. So, there will be a SiO minus layer and they have a diameter of about 100 micrometers. So, this here and this right here are the two channels, right, and the channel lengths are actually depicted in the figure. So, the length here is 10 mm between, let us say 3 and there is a point of intersection, let us say 0. Okay. So, between 3 and 0 the length of the channel is 10 mm, between 4 and 0 it is 100 mm, between 1 and 0 and 2 and 0 both are same 20 mm each. Okay. So, that is how this pumping network is being laid out. These essentially are the reservoirs 1, 2, 3 and 4, and we have the following measurements. So, if we measure the electrical impedance across ports 1 and 2, that means this port right here and this port right here, it results in 400 mega ohms of resistance, and the potentials at ports 1, 2, 3, 4 are respectively 1000 volts, 1500 volts and 0 volts respectively. So, let me just write that down here. So, the potential at port 1 is about 1000 volts of applied potential, same goes true for port 2, another 1000 volts, and then port 3 it is about 1500 volts and port 4 is about 0 volts. So, there is essentially no potential applied on port 4. So, the zeta potential here is assumed to be about minus 100 millivolts, as can be defined by the surface in connection to another liquid phase, and you have to determine the direction of the and the flow rate of the electrokinetic flow formulated in this case in the longest channel, that is the one which measures about 100 millimeters, or this channel between 0 and port 4. Okay. So, the viscosity and relative dielectric constant of the fluids are given to be 0.001 kg meter second and 50 respectively, and the dielectric constant of vacuum is found to be 8.85 10 to the power of minus 40 farad per centimeter.